The Schwerer Gustav, also known as Dora, was the largest piece of artillery ever used in combat. During World War II, it was deployed to destroy heavily fortified Soviet positions. The weapon was so massive that it required 5 dedicated trains to transport it and more than 4,000 personnel to assemble and operate it. Even preparing a firing position could take up to 6 weeks. The armor-piercing shells it fired created craters large enough to swallow entire buildings. Its high explosive rounds could bury themselves tens of meters into the ground before detonating. We've recreated Dora in detail to demonstrate its immense power and to explain why, despite its size and engineering, it ultimately failed to deliver practical success for the Germans. My name is David Webb, and this is Blue Paw Print. The Schwerer Gustav, or Heavy Gustav, was a railway gun engineered by the Krupp Company under the leadership of Gustav Krupp. When fully assembled, the weapon measured 155 feet 2 inches, or 47.3 meters in length, roughly the same as placing 8 M4 Sherman tanks end to end. The barrel alone was an astonishing 106 feet 8 inches, or 32.5 meters long. The gun had a nominal caliber of 31.8 inches, or 817 millimeters, making it one of the largest ever built. Its barrel was rifled with an initial groove depth of approximately 0.4 inches or 1 centimeter. However, continuous firing caused the rifling to erode, gradually increasing the caliber to over 32.2 inches or 817 millimeters. The carriage supporting the gun measured 23 feet 4 inches, or 7.1 meters in width, requiring 2 pairs of parallel railway tracks for stability. With the barrel lowered into the loading position, the total height of the weapon reached 38 feet 1 inch, or 11.6 meters, nearly the height of 4 M4 Sherman tanks stacked vertically. The barrel assembly alone weighed around 400 tons, while the entire system had a total weight of approximately 1,350 tons, heavier than a fully loaded passenger train. To transport such a massive weapon, it had to be dismantled into roughly 25 major components. Deployment began with the construction of 4 parallel railway tracks. The 2 central tracks supported the gun itself, while the outer tracks allowed large gantry cranes manufactured by Ardeltwerke to move and position the components. The railway sleepers beneath all 4 tracks were placed close together and reinforced with iron grids. This was necessary to absorb the enormous recoil forces generated when the gun was fired.
The assembly process followed a strict sequence and required around 250 personnel working simultaneously. First, the left and right chassis halves were assembled. Each half rested on 4 5-axle bogies, meaning the entire gun moved on a total of 40 axles or 80 wheels. Once both chassis halves were completed, a central connection and mounting structure was installed between them. This formed the main support for the gun system. After that, the gun cradle was mounted onto this central structure. The cradle itself was supported by 2 large trunnions positioned between the upper carriage beams, allowing the barrel to elevate during firing. Next, a massive jacket tube was installed into the cradle. This component served as structural support for the barrel and helped distribute stress during firing. The barrel itself was constructed in 2 primary sections, which were joined together using a giant threaded coupling positioned at the midpoint. The rear section of the barrel was enclosed within the jacket tube for additional stability. To manage the immense recoil forces generated during firing, 4 recoil cylinders were installed around the cradle in 2 pairs. These cylinders absorbed and distributed the recoil energy, reducing stress on the carriage and improving structural integrity. Finally, the breech block was moved into position and installed at the rear of the barrel.
This component was essential for sealing the chamber and allowing controlled ignition of the propellant charges. At the rear of the gun, a large loading platform was integrated into the carriage. This platform included two hoists used to lift shells and propellant charges into position. It also featured a self-contained power unit to operate the gun's mechanical systems, as well as a central loading tray equipped with a powered rammer to push the shells into the chamber. The entire system was powered by an onboard diesel-electric generator, which supplied energy to the various mechanisms required for operation. To control the movement of the 1,350-ton weapon, railcar handbrakes were installed on the forward ends of the front bogies. In addition, massive jack pads were fitted to the carriage. Before firing, these pads were lowered to transfer the recoil forces directly into the ground, reducing stress on the wheels and preventing horizontal movement. The Schwerer Gustav fired two primary types of ammunition. The first was the high-explosive shell, known as the Sprenggranate. This was the lighter of the two shell types. Including all components, the complete round measured 27 feet 1 inch, or 8.26 meters in length, roughly the size of a classic London double-decker bus. The shell itself measured 11 feet 4 inches, or 3.45 meters long, and weighed approximately 10,600 pounds, or 4,800 kilograms. It featured a thick steel body designed to withstand extreme pressure during firing. The high-explosive shell was equipped with a ballistic cap made from silicon and aluminum alloy. This cap improved aerodynamics, reduced air resistance, and allowed the shell to travel further. It also concealed the nose fuse. To reduce the risk of a dud, a second fuse was installed at the base of the shell. The explosive charge consisted of hexogen and nitroguanidine, weighing roughly 882 pounds, or 400 kilograms. Hexogen was positioned around the fuse, ensuring it detonated first, which then triggered the less sensitive nitroguanidine. 3 pairs of driving bands made from sintered iron wrapped around the shell and engaged the rifling inside the barrel. These bands caused the shell to spin as it accelerated down the barrel, stabilizing flight and sealing propellant gases behind the projectile. With the maximum powder charge, the shell achieved a muzzle velocity of approximately 2,700 feet per second, or 820 meters per second, giving it a maximum range of about 29 miles, or 47 kilometers. Upon impact, the craters created were roughly 39 feet or 12 meters wide and 39 feet or 12 meters deep in packed earth. The second type of ammunition was the armor-piercing shell, or Panzergranate, designed specifically for penetrating fortifications. This heavier projectile was sometimes referred to as the concrete-busting shell. Its total length was 22 feet 3 inches, or 6.79 meters, and weighed around 15,700 pounds, or 7,100 kilograms, comparable in weight to a P-47D Thunderbolt aircraft. While similar in appearance to the high-explosive round, the armor-piercing shell had a hardened point beneath the ballistic cap and only a single fuse in the base to maintain structural integrity for penetration. Its explosive content was about 441 pounds, or 200 kilograms, using a smaller quantity of hexogen and nitroguanidine than the high-explosive round due to thicker walls. Both types of ammunition were fired using smokeless nitrocellulose powder. The main charge, housed in a steel or brass casing, weighed 2,028 pounds, or 920 kilograms. Additional bagged charges could be added, bringing the total propellant load to approximately 4,080 pounds, or 1,850 kilograms, for armor-piercing shells, and 4,387 pounds, or 1,990 kilograms, for high-explosive rounds. The gun could fire at angles between roughly 45 degrees and 65 degrees. To load, the barrel was lowered to near horizontal, around 10 degrees or less, to allow safe access to the breech. There was no turret. Aiming left or right required moving the entire weapon along a curved section of track. Diesel-electric locomotives pushed or pulled the gun along this curve to align it with the target. Fine adjustments were made using electric motors on certain axles, achieving precision within about 0.4 inches or 1 centimeter along the rails. The crew lifted shells from ammunition cars on the rear tracks to the loading platform using 2 hoists. Shells were rolled onto the central loading tray and rammed into the chamber with a powered rammer. Bagged charges followed, then the cartridge case with the main charge. After sealing the breech, the barrel was raised to the firing angle and the ammunition cars were moved back. The firing mechanism was triggered remotely with an electrical striker igniting the primer.
When the Schwerer Gustav fired, the blast was enormous. The shock wave shattered windows several kilometers away, and the sound could be heard up to 22 miles distant. Local Soviet partisans often mistook the firing for large-scale excavation or mining operations, unaware that they were witnessing artillery fire. After firing, the crew returned to the gun, lowered the barrel back into the loading position, and removed the spent casing using the hoist system. Observers stationed in tethered balloons several kilometers away tracked the shell impacts. They relayed corrections to the gun crew, enabling precise adjustments. Under ideal conditions, with a highly trained crew, the Gustav could fire 1 round approximately every 19 minutes. However, in real combat, intervals often stretched to 45 minutes or more. The busiest day of firing saw only 16 rounds discharged, despite the massive manpower and logistics involved. Recoil damage to the rail bed and preparation requirements often enforced multi-day pauses between shots. The force of each blast compacted the ground beneath the rails by 2 to 3 inches, 5 to 7 centimeters, requiring re-leveling before subsequent firings. The Schwerer Gustav saw action during the German siege of Sevastopol in June 1942. One notable target was the underground ammunition depot at Cukarnaya Balka, known as Weiss Klippens or White Cliffs to the Germans. When correctly aimed, the gun's destructive power was devastating. A single round could demolish piers, collapse overlying terrain, destroy nearby structures, and even capsize small vessels anchored near the impact zone. However, accuracy suffered due to barrel wear, and the originally estimated service life of 300 rounds per barrel was later revised to just 100 rounds. The gun was also extraordinarily expensive, costing roughly 10 million Reichsmarks. This amount equaled the price of 250 heavy 15-centimeter howitzers, 40 Tiger I tanks, or nearly 2,000 V-1 flying bombs. Despite its technical sophistication, Gustav was operationally inefficient. It was slow to deploy, had a very low firing rate, and required an enormous crew for a relatively small number of accurate hits. For example, during the Sevastopol campaign, only 10 rounds landed within 225 feet of their intended targets. Moving the gun with 5 trains and preparing a firing position over 6 weeks was practically impossible without Allied detection. Ultimately, the Schwerer Gustav was a weapon designed for a type of siege warfare that had already become obsolete. After the war, the gun was dismantled and never recovered intact. Its components were scattered and scrapped, and no complete example survives today. Despite its impracticality, the Gustav remains one of the most impressive engineering feats of military history. Its sheer size, firepower, and complex deployment make it a symbol of the extremes of wartime engineering. It is studied not only for its technological achievements, but also as a cautionary example of over-engineering in combat situations. If you spot any errors or wish to add details, leave a comment below.
For more terrifying weapons, check out our video on the V3 Nazi supergun, which was designed to fire shells across the English Channel at London.